Actually, pada dalam komitmen yang sebuah proses using entities, and it is denoted by the element CCR quantity space Q1. Quantitative quantum mechanics in short form. This is why research is the space. Therefore, you can go for the push to okay, so the thesis using splinters and the distance actually is and then this plus so we have the idea C complex person also that inside so
even so, okay, now we have and the question number 9 is a research agenda. Therefore, we have to keep different including this is our product. So product functionality. So and dot mean device one. Therefore, this API. So we have this step and then the combination of between the product and this element. Here's what we have. With the same technical. Yes, thank you. Which is very much difficult as the festival actually has complete with and therefore so we and use this and so this different and then so we have so we have key compute and it is that's one can be higher.
Question number 19 and equation number 14. Okay, question number 19, question number 14. Describing our free space. And of course, in this case, we're talking about the two-state space. Okay, talking about the Dyson quantization scheme, actually, he tried to develop the quantization based on the group. Okay, based on the group. And of course, the group that we have here is describing the free space of the system. And of course, the system here is the free space. So it also influences our canonical group as well. Okay. From the previous discussion, one takes the algebra of the system is this one. I mean, cross R2 theta here, where R2 theta is non-commutative complication space. Okay. Therefore, to develop Hammond equivalent between Lie algebra of Lie algebra here, mean this algebra, and deform mechanical observable, we apply a deform moment map here. We put as a tilde here. I mean, we deform this one, and then because we have a new binary product here, I mean, the bracket start in bracket and start opposite bracket. Where in result equation number 20, the cos cycle obsession follows. Actually, if you notice one, it already similar with the Heisenberg group. Heisenberg group, yes, Heisenberg group for plane. Okay. But the difference is we have a star product here. It doesn't change. I mean, doesn't have any cos cycle respect to position. Okay. Finally, we have a Heisenberg group with star product. Okay. So I put as H2 theta star product as a canonical group for this free space. So we have canonical group for this free space, and then it satisfies our title, our research title, our our presentation title and Canonical Group for the space. So we have this one already done. So this is our Canonical Group, and the first equation number 22a is the algebra, which is Starly algebra, and then 22b is group composition in star pronoun. So we have this one. We do not have any cocycle, any cocycle. It raised, it belong to element C lah, element C. Belong to the center SSC. And then representation. Now we go to representation. Okay. The nice thing about the action representation is, quite mathematical for me, because first we find the group first, and then we seek. We try to develop the unitary representation based on the group that we have, and of course the group here is subgroup subgroup. And after that, it will be develop what we call it contour operator. Yes, that's how Isom's quantization scheme works. Therefore, we define what we call it as unitary irreducible representation. Define the following subgroup. So, in the following operator. So we have this group and this group, this subgroup and this subgroup. And then we certify the following relations. Okay, relation. Equation number 24. Okay, including the star product. Okay, star product. And then after that, equation number 24, we produce the following CCR. So this is our CCR 25. Equation 25. Okay. So we have CCR for quantum mechanics. But in this case, non-commutative quantum mechanics. And then we define a Hilbert space of representation of this one is given by this. Okay? And then the action of the given representation will be this one, equation number 26, A and B. Okay, and lastly, okay. There is something here. Okay, sorry about my fault. Yeah. Actually Q star here, and then this, and then we have another P here, and then D over DQ actually, H bar. Okay, H bar. Okay, I think that's all, because we have this my last slide. Okay, so actually based on the title is first I try to find the canonical group from canonical group for the two-step phase space. So therefore, I have to develop the phase space that will be twisted, that already twisted. Then I find the canonical group, and then I follow the Isom's quantization scheme to find the representation. And representation should be irreducibility and also unitary. So that's all from me. Any question from the audience?
So I see your name is also referred to as, huh? Your slides. Oh, sorry, forgotten about that. In your slides, your name is also being Drinfeld Twist, right?
Yeah, I know that question.
You get what I mean?
What? Again?
Your name has a Drinfeld twist.
I put my F here. Yeah.
Okay. So questions from the rest. Please raise your hand or no, ask directly.
Okay, please welcome.
Physically, what does the twisted face mean? I'm still not get the idea of twisted. We
Okay.
can clarify.
First of all, twisted actually just to make the system is I mean just a twist, the word twist. We would like to twist the system become a non-competitive twist, a non-competitive system. And to make non-competitive system, we apply the third twist. Okay? And the third twist basically takes the half algebra element, And in this case, in my case, my half algebra here is universal enveloping algebra, and universal algebra occurs on the vector field, my vector field. I mean, the physical. I mean, if you're talking about the physical situation, is I do not know much about this one, but for me, I would like to develop the non-competitive system using a different twist. And then after that, I apply the Aisham's quantization scheme.
Okay, any other questions? See in the chat. Nothing there. Anyone else? Uh, some of you have actually attended the advanced maths physics. So we have not actually touched upon universal enveloping algebra, but we have touched upon ideals. So I'm pretty sure there must be some questions there.
It also related to module that you have discussed in your advanced mathematics.
No questions? Okay, maybe because I'm a student, so I'm still learning about all these algebras. The ideal that you have actually chosen, you have not pointed out what is the ideal. So what is the ideal here?
The idea, okay, first, my idea here, okay, wait. My idea here actually, I would like to twist the phase space here. Okay, I would like to twist the phase space. And then, because the twisted phase space imply the non-competitive space, non-competitive position in our phase space. Okay, and then so I follow the Asheri framework. That's my point. I follow the Asheri framework, and I see the how he produced for the non-competitive classical mechanics. And I say, oh, this one very nice because we can also apply the Asian quantization scheme for the star classical mechanics. So I just apply the classical phase space that he obtained in the fetus, and then I I extend into the Asian quantization scheme. I feel it, it probably seem easier for me to obtain the canonical group with star product.
Fauzi, the question is not about your idea, but ideal, the two-sided ideal that you have.
The idea, okay, okay. The ideal actually, as far as I know, the idea is
So what are the ideals that you are forming?
uh, my idea is the element here is we have minus. Actually, lastly, universal algebra actually has the information for something like a algebra, but in the other way, as far that I know. Minus. Okay. And then after that, so we have a tensor, right? We have a tensor f equal to 1 and then plus and then so on. And then the question get something like this one. Okay. So it implies that something like the algebra. So the idea is the element of this, and then the tensor algebra is this one, and then the quotient, I mean the part of this tensor algebra become like this one.
So any other questions?
Sorry?
I'm asking from the rest. Any other questions? Aqua?
So, Fauzi, can you hear me?
Oh yeah, sure.
I want to ask about Hopf algebra. Actually, the Hopf algebra is a pi algebra, right?
By right. Actually, not just by, but it's also have antipode.
What I want to ask, what is the antipode?
Antipode, actually, the kind of inverse. I mean, we include. Okay, actually, we have by algebra, right? So algebra, and the inverse is co-ed. And then for the unitary, co is co-inverse. And for the inverse, actually, inverse that we already know, uh, in terms of the is co-inverse, and the co-inverse in this case is and I mean, yeah, the name that it has co-inverse. I mean, the kind of, I mean, inverse on the co-element, yeah, betul.
Matt? Go ahead. Ahmad.
Can you show your slide? Fauzi?
Okay, sure.
Yeah. Okay. You did mention about the non-commutative manifold.
Yeah.
So I'm not quite clear on that. So can you how does this algebra and related to the non-commutative manifold?
Actually, the twisted principles that we have here will twist the manifold to make the manifold in terms of only planar only plane. It will develop what we call it now between position x and y in that manifold in terms of plane. So that's why I'm not talking about non-competitive manifold by island rules, but in this one, based on the information theory from the actually framework.
So does this algebra give your structure?
Yeah, and it develop a new structure, which is leads to the
Okay, probably if, can you go back to the when you start doing the co-cycle thing? Now I'm a bit confused here. Here in your equation 21 is purely a Heisenberg group. Okay, but you also had that what you call central element that appears between the commutative, well, between the Poisson bracket of your position.
Right.
Okay, so why is this not appearing here?
What do you mean? I mean, actually, star product here actually produce another. Okay, this star product actually produce this one. Actually, I already showed the calculation here. This one produce another. I mean, the kind of synthesization. But
Okay,
unfortunately, for the
can
Poisson bracket also produce the same one. So they both will vanish each other, and the rest is this one only. So this one is why I treat as a co-cycle obsession.
hang on. When you had that the Lie algebra thing, okay, with the star product, everything to be commutative, right?
That's a good question. Yes.
And then your
Okay.
Poisson bracket, there are two relations which is not commutative. So how is this not reflected here?
Uh, for this back actually this if you notice this one without star product this Libreca is commutative. But if we have star product here, this Libreca will have another I mean not commutative not commutative. But for this case, this case is related to the previous equation here.
Okay,
We apply.
can you go to the previous slide? Yeah. So over here, if we look at equation 14, so everything is commutative under the star product.
Okay, everything is commutative here because this one is vector field, not the element Q. I mean the Q itself. Because if you notice this one, P, okay, P, okay, what is P mean here? Yeah. Okay, P here is here is AI here actually produce the canonical this one AI actually not vector field bukan vector field tapi dia menghasilkan PI again and then plus PI and then eh,
Just control Z.
QI. Okay. For my case, I deform the moment map here. We have like this one PI capital letter and BI QI capital letter. This is what P map means. Okay, from the Isham scheme. So this one Hamilton with the field, FB, and this one is function, and then this one is J map, and this one to this one is P map. So this one Lie algebra, and this one is gamma map. So from Lie algebra to which is QI and PI. That's why how moment map means. Not PI, not this one. this one. Talking about the moment map develop mechanical observable. Okay, if you're talking about this one, actually this one should be certified for the gamma map. This one, for the gamma map. Yes, for the P map, no, we develop Q and P, mechanical observable.
So what is the Lie algebra that being produced? Because it's not quite clear when you switch to this star product. What is the essential algebra that you want to take the canonical group from?
Okay, this one I already say this one is not r theta square, not r theta, not r square, but r theta square. So we have another element that this one is already discussed previously. Yeah, we already discussed about how we develop this one.
So that means essentially your algebra is already having the
Centralization of that.
central extension for the non-commutative position.
Right.
So what's left is essentially you're just trying to impose the central extension from quantum mechanics.
Yeah, something like the ordinary quantum mechanics ada. Just Heisenberg group. Nothing special on my work actually. So actually same Heisenberg tak apa lah, same. But the new one is I include a star product. But for me macam look funny lah, because just include the star product gitu je.
Okay, Ahmad.
So,
Okay, Mat. Okay.
if it is the same, so what's new by using Isham conversation and apply in the case of
Okay, the new
what
one
do you think that we can learn from?
actually first certify the certify what the author has done using a star product, because my way is through the action quantization scale. But for the in literature, they just put the star product and then they're happy about their star product. And then for me, just I try to get where is get the answer. And then the next thing about Heisenberg here is before this we only had the piecewise, point product, point wise product, the ordinary product, yang biasa tu. And in this case, I have another a new product, and I call it a star product. So my Heisenberg group is I call it. That's why I would like to call this one as deformed mechanical group, because I deform the mechanical group itself.
Faudzi, normally when it depends on which school of the literature that one normally writes in this particular case the Lie algebra. I'm not sure whether I cannot see. Okay, the star product, that star product.
Tulis oh ya.
Sorry, I didn't have. I don't think I can present, right? Because you're presenting.
Okay, I can stop right now.
Okay, in that case, I have to plug in my tablet. Just hang on a minute. So let me do this. Hang on. They hang it up. The thing, can you guys see this? Okay, Fuzzy, I was referring to, if I'm not mistaken, you had something which is as ish. Ish 2 theta or something, and then you put a star product. Now this is would be in the sense of you're trying to say what multiplication that is, right? But the normal sense of what you call when you say a particular group, no, let's say G, and then essentially you have your Lie algebra, usually represented by a commutator. Now, I'm not sure whether one should be indicating this or one should be indicating this. Okay, so in other words, one should rather write something like with respect to this star commutator, for example, because this one you would see appearing in the deformation quantization thing. So in other words, the quantized thing is essentially you deform the product. Okay, but in the case of the way that Chris Isham is doing his quantization thing, the one that we are actually quantizing is the Lie algebra part. Okay, so the way that you have done this is more towards the deformation quantization notation. Okay. The other thing that I should make comments is that in Chris Isham's way of doing things, you don't need to invoke any universal enveloping algebra. Okay. So in a way, what you had put in, what you had suggested, essentially you include elements of algebra that was not really there before. So things like why do you need a Hopf algebra inside the system? There's no such thing inside Chris Isham quantization. So that's why I think I mentioned this to you before. The problem with this is essentially you put some extra ingredients inside your quantization program, which in this case you are using Chris Isham's quantization program. So in other words, the justification has to be there in some way, or you generalize the idea of Chris Isham to include, say, universal enveloping algebra or something like that. Okay. So these are not very clear to me, so I think probably these are points to be clarified. Okay. So I stop sharing that. So any other questions from the rest? So let's see. I need to stop my recording soon. No more questions? Ahmad, the
Maybe one possible question. No, this is just for money. Can we generalize to the mod? Like fiber bundle and so on.
No, actually I did not looking on that one because I just because I'm involved in this non-competitive, and non-competitive always play around with the plane, no? Plane, not on the sphere of Taurus. Actually, they are mostly in on the plane. I mean, just R2 only. Okay. So that's why I'm interested in the plane only, lah, rather than the fiber bundle or anything else.
okay, Aqua. I saw you raise your hands. No.
So you raise your hand.
So I want to ask about universal algebra. So actually, what is universal algebra?
Okay, the simple one is about he has the associative, and also
Okay.
unital. If you notice, the algebra doesn't have associative, right?
I don't know.
No, the algebra doesn't have associative. So only universal algebra only has associative condition. Yeah.
Okay,
I
what?
thought
So-
algebra they replace the associative with the properties.
Can you repeat again?
I thought the Lie algebra they replace the associative properties with Jacobi identity.
Oh, I don't know. So far as I know, there is no associative condition, right? Only group that has associative.
Yep.
If you're talking about the one, maybe just only Jacobi lah, just only.
Mm.
But Jacobi, we have a 3 terms, right? And then the rest. Right.
Thank you.
Okay. Anyone else? One last shot.
One last.
Okay, Ahmad.
No, because I found a paper by the author that you mentioned about. He talked about this age group of non-competitive principal bundle and twist deformation.
Yeah.
That's why I asked about that.
Yeah. Actually, I tried to understand, but that one, but it's because there is a lot of notation for me. I mean, I'm not familiar with the symbol and notation, and also I have to understand. Actually, okay. So far, I would like to discuss about my representation that I have here is not something vector space on, but we call it as a module representation because the representation usually include the ring. Oh, that's why I don't want to talk about this one much. Because I just have a representation, then that's all.
The paper, he also talked about co-module.
Yeah, co-module, right? Co-module. Because call back to the module.
So there are a lot of new things. I
Yeah.
understand.
I guess probably the point is maybe I want to wrap up. Probably some of the things that you have said requires some kind of precise definition and refinement, because again my worry is always this. I've mentioned this several times already, is when you bring together two different quantization approach, you have to make a choice in some sense. What is the fundamental thing? Okay, so either you're thinking like just now, for example, when you use notation, okay, when you use the notation, you had put in your product as as the pair with the group, or in some sense is your manifold, okay, but that is actually emphasizing the deformation quantization kind of school. So one has to be careful in this kind of thing. So you need to be able to tell us what is the more fundamental thing. So these are things I believe it's not, personally it's still really not clear, and this probably might need some clarification from you. So this is my thoughts, but I'm not sure about the rest. Anyone else want to say something? Fauzi, last words. Anything you want to say? Yeah.
Actually, I would like to clarify your question. Actually, my fundamental is canonical group composition. Okay, canonical group composition. The deformation applied here is I would like to deform the position in terms of the classical, in the classical form. I mean, so therefore that I have here right now is deform Calais classical mechanics.
Yeah,
So that's why.
but again,
Uh,
you see, when you deform those, the deformation is actually with respect to the ordinary product, not the Lie product. Okay, so that's why when you deform the product and then you do the Lie product, the Lie product changes. Okay, so these are things are not so quite clear to us. What remains a fundamental thing and what should be the final thing to say. So these are again, no, I believe you also now we have discussed this several times. It just needs a bit more justification and clarification, I think. So again, with respect, when you talk about modules, no, one has to be very clear what you're saying. Okay, what with respect to what rings that you're looking at. Okay, so these are things are probably not quite clear. So